All right, let's have a quick introduction here before we go into solving problems. A linear equation is an equation that represents a straight line when plotted on a graph. And in algebraic terms, a linear equation in n variables would be represented in such a way that the variables will be the total number of the variables will be the numbers of the variable contained. Let's say you have 10 variables, so variable 1 can be x1, variable 2 can be x2, variable 3 can be x3, and so on and so forth until you get to x10. And this can be represented in such a way that each of the variables have coefficients. So if that is the case, then the coefficient of each of the variables comes just before the variable. And usually, linear equations, the summation of such variables will be equal to a constant term in this form. All right, let's consider an example. Consider the following system of linear equation. We have two variables in this case, x and y, and of course it can be x1, x2, x3, x4, and so on and so forth. But for this system, we have just two variables, not 10 variables, not 3 variables or 4 variables as the case may be. All right, so then the variables we've got here are simply x and y variables. And of course, you can see that the sum of the coefficients of each of the variables and their variables equal to a constant term in this form. So, and of course, this system of linear equation can be written in form of matrix as this, where A is the matrix that represents the coefficients of each of the variable, and X represents the variable, while B represents the constant terms. All right, let's look at the form in which the solution to systems of linear equation can take. Now, a system of linear equation can have one of the following types of solution. It can have unique solution. Unique solution shows that, well, there is a definite solution, in the sense that if the coefficient of the matrix that the system of linear equation forms is not singular, in other words, the determinant is not 0. So this means that the system would have only one set of variable values for the variables that makes the equation true. This is repetition here, please take note of that. All right, so that means that for when you solve this, and let's say x equals to a particular value, when you substitute that value in here, the linear equation would be true. I mean, when you get a value for x, you get a value for y, and you substitute into each of these equations, you'll discover that when you add them, you will get 6. And when you perform this operation also on after substituting for x and y, you will also get 5. So that means you have one set of values for the variables, and that makes the equation true. Okay, that is for unique solution kind of system of linear equations. Another set of solution that is possible is no solution. So it is possible for a system of linear equation not to have solution, and that occurs if the equation represents parallel lines, that is in case of two variables, or planes in the case of three variables, that do not intersect. So this occurs when the system is inconsistent. So we encounter such inconsistent situation maybe when a problem is badly formulated, or there's an error in the problem. So you get a situation where there is no solution to the problem. For example, take for example this system of linear equation. Now if I say solve for x, how do you achieve that? How do you achieve that? So basically, this kind of system of linear equation does not have solution. When you tend to subtract, maybe you substitute for x or you substitute for y, you'll see that that will be practically impossible. So that's another kind of solution. So the third kind of solution is infinite solution. So this occurs when the determinant is 0. So we say a system has infinitely many solutions if the equation are dependent, meaning they represent the same lines or plane. So, and it generally occurs when the determinant is equal to 0. So basically, from these three kinds of solutions that are possible, only unique solution kind of system of linear equation can be true when they are solved. So an example of a system of linear equation with infinite solution is when you have one of the equation in the systems being the multiple of the other. For example, in this system of linear equation, you can see the second equation here is a multiple of the first. So in such kind of cases, the equations are linearly dependent, the solution sets will become infinite, and the consequences are usually that there cannot be any unique solution. Moreover, in some cases, the systems would have multiple solution, or solution may even depend on various parameters. So that is usually not a case to well, often desire. All right, let's then move on to looking at methods for solving systems of linear equation. We'll be talking about 5 different methods of solving linear equations: substitution method, elimination method, Gaussian elimination method, matrix inversion method, and Cramer's rule. So let's start from the first method, substitution method. I think this method should be common. When you have a system of linear equation as this, substitution method, you first of all solve for the first equation, and you just make one of the variables the subject. You substitute for one of the variables. So here you can subtract both sides, x from both sides, so you can then have y equals 7 minus x. So then you substitute for y in the second equation. So that is what we've done here. that is 2x, y is 7 minus x, so we substitute that in here, and simplifying this would result in x being equal to 8 all over 3. So, and after getting x, what you then do is to substitute x back into any of the expressions, or particularly the expression for y. So when you do that, particularly in this case, that will be 7 minus 8 all over 3. So solving that would give y equal 13 all over 3. So the second method for solving systems of linear equation is elimination method. So in elimination method, basically it involves adding or subtracting equations to eliminate one of the variables, making it easier to solve for the remaining variables. Let's take, for example, this system of linear equation. So how do you handle that? Via solving using elimination method. So you multiply, you look at it, and you look at a simple way of eliminating one of the variables so that it will be easy to solve the problem. So the easiest way is to multiply this second equation by 2. So doing that will transform this equation, 4x minus y equals 19. When multiplied by 2 will give 8x minus 2y equals 18. And of course we can now subtract, we can now add this equation and this equation to eliminate y variable. So if done correctly, adding the two equations, 11x will then equal 30. So dividing both sides by 11 will give x equal 30 all over 11. So we can then substitute this back into the original equation, any of the original equations of course, to get y. So taking this second equation, which should be the simplest, with which the substitution can be made, so that was 4x, and since x is 30 all over 11, then we get something like this. So we can then say subtract, or maybe add y to both sides and subtract 9 from both sides, and if we do that, we have y equals 4 times 30, that will give us 120 all over 11. So minus 11. You can just bring this y to this side and bring 9 to this side, and when it crosses this equal sign, the sign here would become positive, and this is positive 9 here. When it crosses this equal sign, it simply becomes a negative. So that is just what we've got here. Now playing around with this will give y equal 21 all over 11, and that's the solution we've got here. Alright, these examples are really elementary, but never mind, we'll be moving up higher into higher order of systems of linear equation in the next slide. So but we just need to start from the elementary in order to freshen up well, or reflect on our past knowledge on all these systems of linear equations. So the third method that can be used is matrix inversion method. So where the system of linear equation is written in form of matrix, in this form, ax equals b. So, and the solution to the system of linear equation will be such that x equal the inverse of matrix A times B. So writing the system of linear equation in the form AX equals B will give A, of course, A is the elements of A would represent the coefficients of the variables. The coefficient of variable X is 2 and 4. 2 and 4. The coefficient of variable Y is 3 and 7. 3 and 7. So that forms the elements of matrix A. So the variables, we've got just two variables, X and Y, and the vector part, that's B, the constants values, that is the these values here. So, and that is the B part. All right then, so we then find the inverse of this matrix. The inverse of this matrix can be found by exchanging these two elements. So 7 comes up here and 2 comes down here, and we simply change the sign of these. So after doing that, basically using adjunct method, we then divide all what we've got in all the elements in the matrix by the determinant of the matrix. So the determinant of this matrix is 2. That is 7 times 2 minus 4 times 3. That will give us 2. So, and when we alternate this and change the signs of this and divide by the determinants, this is what we get, and that gives us the inverse of the matrix. So the variables now, X, will then be multiplying this inverse by the constant values. Now, if rightly done, X will give us 5 all over 2 and Y will give us 2. Basically, I think we've looked at this example in our previous class. Like I told you, we are just trying to freshen up with these elementary examples. Okay, let's move on from here. Okay, let's see how far you can go on your own. Can you just try to solve this problem, this system of linear equation, using these 5 different methods? All right, maybe if you are not familiar with any of these methods, never mind, in the next couple of slides, you should be able to solve this system of linear equation using all these methods. And of course, each of the methods should produce the same answer, the same value for each of the variables in this problem. All right, here we go. Let's start by using matrix inversion method to solve this system of linear equation. So let's start by expressing the system of linear equation, the system of linear equation in matrix form. That is AX equals B, and this is the matrix form of this linear equation, and this is the matrix A. This is matrix X, showing the variables contained X, Y, Z, and this is the constant values 6, 14, and 1. So the next thing we do is to find the variables by multiplying inverse of the matrix by the constant values. So the task ahead now is to determine the inverse of this matrix. Do not forget, using adjunct method of determining the inverse of a matrix, the inverse of this matrix will equal 1 all over the determinant of this matrix times the adjunct of this matrix. So the next thing to do now is to find the determinant of this matrix. So using the method earlier discussed, so we simply compute the determinant of this matrix, and if done well, the determinant will equal 11. And since of course the determinant is non-zero, that means the matrix A has an inverse. That means it has a unique solution. Alright, the next step is to find the inverse of matrix A. So, and recall that the inverse of matrix A equals 1 all over the determinant of matrix A all over adjunct or adjugate of matrix A. So how do we transform the elements in matrix A to its adjunct? So let's just quickly explain that. Now the idea here is to form the adjuncts from the minus of 2 by 2 matrices that will be produced as we work on the elements of matrix A. So let's take the first element, that is the first element on the first row and the first column. So we can cover the row relative to the first element and the column relative to the first element. So we have the minor 2 by 2 matrix. So the determinant of this matrix will form the first element in the adjunct matrix here. So the second element in this adjunct matrix is found by shifting from the first row to the second row. So we just cover the elements in the second row to form the next minor. But this time around, we alternate the sign. So by alternating the sign, the matrix formed by this minor, instead of BI minus HC, will then be HC minus BI, and that is what we've got here. So moving on from there, we also now cover the elements in the third row to form the next minor of 2 by 2 matrix. So the determinant of this, because we've alternated the sign of the next second one, the next element will not, in the adjunct, will not be alternated. The sign will not be alternated. So the idea is to determine the matrix of the minor for this first element, alternate the sign of the element produced by the minor used in determining the elements for the second one, this second one. Then again, we do not alternate the sign of the elements in the third column of the first row. So the next one is this. We also alternate the sign. You do not alternate the sign of this. So and that is how you move on and on and on. Alternate the sign after the other, and alternate the sign after another, alternate the sign after another, and so on and so forth. So now we do not have to alternate the sign of this, and that is why the determinant will be BF minus CE. So the next thing to do now is to move from the first element in the first row and first column to the second element in the first row and the second column. So first is to cover the row and column relative to the element to form the minor matrix, and the determinant of this matrix will form the next element in the adjunct, do not forget that the sign here now will now be alternated, and that is why we've got the determinant of the minor to be this. So the next thing again is to move from this row this way to form the minor of the matrix, and the determinant of this will not be, the sign will not be alternated, and that is what we've got there. So again, we move down on and on and on to form the minor of the matrix. The sign of this, of course, will be alternated, and that is why you've got CD minus AF. So, and after that, we move on to the third, that is element in the third column and the first row. So again, let's start by covering the elements relative to this third column and first row elements to form the minor of the matrix. So this time around, we are not alternating the determinant of the matrix, and that will give us DH, D time multiplied by H minus E multiplied by G, and that is what we've got here. So the next one, the determinant of the minor of the matrix would be alternated. So, and that will be produced from covering the next row. So, because we're going to alternate the determinants, so that will give us BG minus AH. And that is how we move on to the next and the last one. The determinants here will be alternated, the determinant of the minor. So, and that will be, sorry, the determinant of this one will not be alternated, and that will be AE minus BD. So that is how we get the adjunct of this 3 by 3 matrix. So, and this is the matrix we are talking about. So when you plug in these values into all this to determine the determinant of each of the minors, as earlier explained, if done appropriately, these values should be gotten for each of the elements, and that takes us to the adjunct of matrix A. So then the inverse of matrix A will be 1 over the determinant multiplied by each of the elements in the adjuncts or adjugates. So we then have to multiply 1 over 11 by all the elements to give us the inverse of the matrix. So, and that is what we've got here. So we then move on from here. All right. So the next step is to solve for the variables. So the solution of the variables is determined by multiplying the inverse of the matrix by the constant variables in this form. Therefore, to compute each component of the variable, x will be this element multiplied by this element multiplied by this multiplied by this, for the summation of that gives us x. The summation of multiplication of this element with this element with this element with this gives us y, the value of y, and the value of z is determined by the multiplication of this element with this element with this element with this. So that's just pretty simple. So, well, if done well, appropriately, x will be, the value of x will be 8 all over 11, y will be 9 all over 11, and z will be 49 all over 11. In this video, we will be solving this system of linear equation using substitution method. Of course, in our previous video, we had solved this same system of linear equation using matrix inversion method. Alright, so next we try to solve the same system of linear equation using substitution method. Now for substitution method, we simply solve for one of the variable and substitute that value and substitute that equation in the other equations. So the simplest one equation to pick here in solving for one of the variables, say x, is this equation. So we can solve for x. So x will then be equal to 6 minus y and minus z. So the next step is to substitute for x in the second and third equation. So that means instead of x here, we'll then have 2 multiplied by 6. Instead of x, we then replace x with 6 minus y minus z. Then we continue minus y plus 3z equals 14. So we also do that for where we can expand 2 multiplied by 6, 12. 2 multiplied by minus y will give us 2 minus y. Minus 2y. And 2 multiplied by minus z will give us minus 2z. So we then continue and collect like terms. So collecting like terms shows that minus 2y minus y will give us minus 3y. Then minus 2z plus 3z will give us z. That's plus z. Then we've got 12 here and 14 here. So we collect the like terms, and this comes here to become minus 12, or you can say subtract 12 from both sides. So when we simplify that, we then have minus 3y plus z equals 2. That is 14 minus 12. So then for the next one, we also substitute this value for x in this equation. So that will be 3 into brackets 6 minus y minus z. So we also expand, combine like terms, and move on. So moving on from there, we simplify what we've got, and that will give us y minus 4z equals minus 17. So the third step now will be to solve the two variable system minus 3y plus z equals 2 that we got earlier, and y minus 4z equals minus 17. So we can first of all solve this equation for y. So you make y the subject, and we then get y equals 4z minus 17. That is when you add 4z to both sides of the equation. Minus 4z plus 4z here becomes 0, and 4z plus 4z here will come here, and you see this is minus 17, and that is placed where it belongs as appropriate. So you then again, because we are using substitution method, you can now substitute this for y in this equation, and that is what we've done here. So minus z, then you substitute this for y, and you see by so doing we can expand, collect like terms, and solve for z. So solving for z shows that z equals 49 all over 11. So then we can then substitute this value in any of this equation to get y. So of course, in order to just simply get the value of y directly, because we had already made y the subject here, we can just substitute 49 all over 11 for z here and just play around the equation just as this to get the value of. In this video, we shall be solving this system of linear equation using elimination method. Of course, in our previous video, we had solved this same system of linear equation, this same problem, using matrix inversion method as well as substitution method. Okay, so the third method is to use elimination method in solving same problem. So this time around, we want to use elimination method. Now, to solve this system using elimination method, what we first do is to eliminate variables, the variables step by step until we find the values of x, y, and z. So first step, let's eliminate x from the second and third equation. So this is the second equation, this is the third equation. So in order to eliminate x from this and this, we need to multiply the first equation by 2. So when we multiply the first equation by 2, we get this. So we then subtract the next equation from that. So when we do that, you subtract the left hand side from the left hand side, you subtract the left hand side from the left hand side, and you subtract the right hand side from the right hand side. So this time around, what we are doing, we are subtracting this from this. So and that is why you see this coming first and this coming second. And that is why you see this coming first and this coming second. So you subtract the left hand side from the left hand side, and you subtract the right hand side from the right hand side. And that is what we've done here. So playing around with that, 2x minus 2x will give us nothing. So minus y minus 2y will give us minus 3y. Then 3z minus times plus, of course, will give us minus. So that would be minus 3z, plus 3z minus 2z. That will give us z. That's plus z. So 14 minus 12 will give us 2. So the second equation then becomes minus 3y plus z equals 2. So instead of this is what we've got now. Now the next step is to multiply the first equation by 3 and subtract it from the third equation to eliminate x. We want to eliminate x from these two. So we'll multiply this by 3. So when we multiply this equation by 3, we have this. So and when we subtract it from this, we want to subtract this from this. So, and that is what we have tried to do here. We've written down this, what is on the left hand side minus what is on the left hand side here, and what is on the right hand side, which is 1, minus what we've got here, minus 18. So 3x minus 3x give us 0. So we have successfully eliminated x from the third equation. So then 4y minus 3y gives us y, and minus z minus times plus gives us minus. So we have minus z minus 3z, that will give us minus 4z, equal 1 minus 18, of course, is minus 17. So this is what then occupies the third equation. So the third equation becomes this. So what we then do is that we can then solve for y and z using the new equation, using the new second and third equation, which is this. So again, we can use elimination method. So how do we eliminate? We now want to eliminate y. So how do we eliminate y? We multiply the second equation by 3 and add it to the first equation to eliminate y. Of course, when we multiply 3 to this equation, it will give us 3y minus 3 times minus 4 will give us minus 12z, and equals minus 17 times 3 will give us minus 51. So when we multiply 3 by this equation, we have this, and we can now add it up to this. So that will give us minus 3y plus this equation basically. So this is it. So when we want to add this and this, what is on the left hand side is added, what is on the right hand side is added. So minus 3y plus 3y gives us 0. So z plus times minus will give us minus. So z minus 12z will give us minus 11z equals 2 minus 51 here will give us minus 49. So z equals 49 all over 11. So we can then substitute this back into equation 4. Basically any of the equation, but this will appear simpler. So we can substitute z into equation 4 to determine y. So, and that is what we've done here. You can see y minus 4 into brackets. We substituted this for z, and we played around it sufficiently to determine y, which equals 9 all over 11. And we can also substitute 9 all over 11 for y and 49 all over 11 for z, and substitute into any of the earlier equations to find x. And of course, this is the first equation, which, well, may be the simplest to substitute these values into in order to get x. And that is what we've done here. And well, playing around the equation shows that x equals 8 all over 11. So you can see then that x equals 8 all over 11, y equals 9 all over 11, and z equals 49 all over 11. So looking at the solution, you'll find out that the answers gotten using elimination method is the same with the answers gotten using the substitution method as well as the matrix inversion method. In this video, we would be solving this system of linear equation using Gaussian elimination method. Of course, in our previous videos, we had solved this same problem using matrix inversion method, substitution method, and elimination method. Alright, then next, let's try solving this same problem using Gaussian elimination method this time around. So now Gaussian elimination method is, well, a bit similar to elimination method because we try eliminating the off-diagonal elements in order to narrow down the solution to determining the variables. But here we use augmented matrix form to solve the problem instead of mere elimination method. So the first thing to do is to write the augmented matrix. So this is the first, the matrix form of this system of linear equation is to write down the coefficients of all the variables. So the coefficients of x in the first, second, and third equation here is 1, 2, and 3. So you write 1, 2, and 3. The coefficients of x and the coefficients of y in equation 1, 2, and 3 is 1, minus 1, and 4. So 1, minus 1, and 4. The coefficients of z in equation 1, 2, and 3 is 1, 3, and minus 1. 1, 3, and minus 1. So you then augment that matrix with the constant values. So which is 6, 14, and 1. 6, 14, and 1. So now the next step after this step is to make the first entry in the first column a pivot to eliminate below. Now, like I told you, the off-diagonal elements here, we want to try to eliminate them so that the off-diagonal, this is the diagonal elements, recall? This is the diagonal elements. So the idea is to eliminate the off-diagonal elements, this, and this to become 0, this, and this to become 0, and to ensure that the diagonal element becomes an identity. That's 1, 1, 1 in form of an identity matrix. So we then begin to perform different row operations on each of these matrices and the subsequent matrices, so that this time around we're talking about augmented matrices. So that we achieve the elimination we desire. So now the step here is to make the first entry in the first column a pivot and eliminate the below. So we want to make this the pivot. That is now we won't be transforming this. We want to make this a pivot, and if this is made a pivot, we want to use it to perform row operation on the second row, so that this is the second row for row 2. So row 2 will now be row 2, that is the initial row 2 minus 2 times row 1. So in order to eliminate this element here, we want to multiply minus 2 to multiply 2 to row 1 and then subtract that from row 2. So if we multiply 2 with 2, that's row 1, times 2 gives us 2. So 2 minus 2, of course, will give us 0. All right, row 1 times 2 gives us 2 again. Excuse me. Then minus 1 minus 2 will give us minus 3. Okay, so 1 times 2 will give us 2. 3 minus 2 will give us 1. So, but for this, 2 times 6 will give us 12. So 14 minus 12 will give us 2. So we have successfully, using row 1 as the pivot, and that is why nothing has changed here, we have been able to eliminate the first element in the second row here, the first column. All right, so the next thing is we want to also eliminate the element here, the first column of the third row. So what we do to that is the new row 3 now will be row 3. This is the row 3. Row 3, or we can just move on with this now. So row 3 minus 3 times row 1. Row 3. So we are still using 1 as the pivot, so nothing will change in 1. So now, and of course you can see in this step we are performing 2 row operations together under this step. We are using row 1 as the pivot for this row operation, row 1 as the pivot for this row operation, and we are performing that simultaneously. So instead of doing this 2 augmented matrix, you can just put a comma here and write this row operation and just perform it simultaneously, and you don't have to write the 2 augmented matrix. Just transform this into this and this. So just transform it into this. So now the new row 3 will be row 3, which is this, minus 3 times row 1. So 3 times row 1 is 3 times 1. That's 3 minus 3 will give you 0. So new row 3 is row 3, which is 4, minus 3 times row 1. 3 times 1 is 3. 4 minus 3 will give us 1. So also minus 1 minus 3 times 1. So 3 times 1 is 3. So minus 1 times minus 3 is minus 4. So in the same vein, 3 times row 1 is 3 times 3 times 6, that's 18, and 1 minus 18 will give us minus 17. So we have successfully transformed this element and this element to a 0. We also have to, we are left with transforming this element to 0, this element to 0, this and this also to 0. So the next step now is to make the second row pivots, and we want to eliminate 1, the 1 here. We want to eliminate it. So, okay, we want to make the second row pivots. All right, so we also want to perform 2 row operations simultaneously on this augmented matrix, of course the resulting augmented matrix. What we want to do is to make the second row's pivots a 1, and we want to eliminate the above and below. We want to eliminate this and we want to eliminate this. We want to make this a 1. So in order to make this row a 1, what we do is to divide row 2 by 3. So we just simply divide row 2 by 3. So 0 divided by 3 gives us 0, minus 3 divided by minus 3 gives us 1. Of course, we don't need a minus 1. We need a minus, we don't need a minus 1, we need a 1. So 1 divided by minus 3 will give us minus 1 all over 3, and 2 divided by minus 3 will give us minus 2 all over 3. So we have successfully made this particular element a 1. So next we want to eliminate this and this. So in order to eliminate this now, we perform this row operation by subtracting 1 from 2. Row 1 from row 2. So this is row 1. When you say 1 minus 1, you get 0. So when you say 1 minus 1 all over 3, you get 4 all over 3. So when you say 6 minus 2 all over 3, you get 20 all over 3. So you see that again we've been able to eliminate the element in the second column and first row to become 0. So what we are left to do now is to make the element in the third column and first row and the third column and second row, to make them 0, both 0, and to make the element in the third column and third row 1. So that is what we are going to do next. All right then, so in order to make the element here 0, what we do is subtract row 3 from row 2. And if done appropriately, we should get a 0 here. That's from the previous slide. We should get a 0 here, and the elements we've got represented in each of these various positions. So the fourth step now, just in 4 steps, the fourth step now is to make the third row pivot a 1 and eliminate the above. So you now see that we need to make this element, of course this element have now changed from what it was because we have made this an 0. So now we want to make this a 1 and eliminate what we've got above it, this and this. We want to eliminate them to become 0 and make this 1. In order to make this 1, all we do is divide what we have on row 3 by minus 11 all over 3. So when you divide this by minus 11 all over 3, what you are left with is 1. You then divide this also by minus 11 all over 3, and what you've got is 49 all over 11. So again, in order to eliminate this and this, let's work on eliminating this first. So what we do is to say row 1 minus 4 all over 3 times row 3. So when we perform this row operation on this first row, what we get is we eliminate 4 all over 3 in this third column and first row to become 0, and this augmented part becomes 8 all over 11. So again, we try to eliminate the element in the third column and second row using this row operation. So that gives us for row 2, we simply add row 2 plus 1 all over 3 times row 3. So while performing this row operation on row 2 using row 3 gives us 0 at this point and 9 all over 11 at this point. So what we then have at the end of the day is a situation where we've got, the values of x being equal to 8 all over 11, and the value of y being equals to 9 all over 11, and the value of z equals to 49 all over 11. Now when you compare this solution with the previous solutions, you'll see that the answers are also the same. So basically what we have done is to transform the entire augmented matrix into a row echelon form, and that we have done to get the solution to the system of linear equation. In this video, we will be solving this system of linear equation using the Cramer's rule. Of course, in our previous videos, we had solved this same problem using matrix inversion method, substitution method, elimination method, as well as Gaussian elimination method. Alright, so this time around, we are going to use Cramer's rule to solve the same system of linear equation we have been working on. Earlier, this system of linear equation had been solved using matrix inversion method. It has been solved using substitution method, elimination method, as well as Gaussian elimination method. So this time around, we'll be using Cramer's rule. Now, the idea in the use of Cramer's rule in solving linear equation is transforming it into a matrix form of the form in the form ax equals b, and such that the solution to each variable appears in this form. Okay, let me not confuse you with this. Let's just go straight into solving the problem. Let's transform on the first step. Let's write the system of linear equation in the form ax equals b and compute the determinant of a. So a becomes the coefficient of each of the variables. So the elements in a, for example, the coefficients of variable x is 1, 2, and 3. You can see 1, 2, and 3. The coefficients of variable y is 1, minus 1, and 4, 1, minus 1, and 4. The coefficients of variable z is 1, 3, and minus 1, 1, 3, and minus 1. Of course, for the variable elements, the three variables we've got are x, y, z, and the elements, the constant values, are represented by this vector b: 6, 14, and 1. 6, 14, and 1. Now it is important to also, because that is what Cramer's rule is all about. So what Cramer's rule states, what we are trying to describe here basically, is that you see this is the matrix A, the main matrix component of the system of linear equation. So we then can find AX. And what is the difference between matrix A and matrix AX in this context? You will find out that for AX, the coefficients of X here, the elements that represent the coefficients of X have been replaced by the constant values 6, 14, and 1. So what will then also be the matrix AY will be that the coefficients, the element representing the coefficients of Y would simply be replaced by the constant values 16, 14, and 1. And of course, every other thing will remain as it is in the main matrix form of the system of linear equation. So you see, only the elements represented by the coefficients of X was replaced by the true values in AX, and for AY, only the elements that represents the coefficients of Y have been replaced by the true constants, the constant values. So, and for AZ, look at this. These are the same, these are the same, but the elements that represents the coefficients of the Z have been replaced by the constant value for 6, 14, and 1. So this is your AX, this is your AY, and this is your AZ. Now, Cramer's rule states that the value or the solution of to variable X will be equal to the determinant of AX all over the determinant of A. The solution to variable Y will be the determinant of AY all over the determinant of A. And also, the solution to variable Z will be the determinant of AZ all over the determinant of A. So we said the first step is to write the system of linear equation in this form and compute the determinant. So let's go ahead and compute the determinant of A. So computation of the determinant shows that we've got 1, 1, 1, 1. Of course, you alternate the sign, 1 minus 1 and 1, and you have the minor matrices, and you get the determinant of the minors, and well, playing around with that equation to determine the determinant of, to compute the determinant of A, shows that the determinant of A gives 11. So just play around with that matrix A to compute the determinant, and you will see that the answer is 11. Now, the next step is to compute the determinants of matrices AX, AY, and AZ. So for matrix AX, we want to replace the first column with the constant value 6, 14, and 1, and that we've done here. That is Cramer's rule. So we then find the determinant of AX, and we also play around with this AX matrix to find the determinant to get, and if done appropriately, the value, the answer gives 8. We then move ahead to get the to work on matrix AY. The matrix AY is, well, gotten from matrix A by replacing the second column with the constant values 6, 14, and 1, and that we've done here. So we also find the determinant of AY, and that gives us 9. Right then, so moving on from there, we also get matrix AZ by replacing the third column with the constants 6, 14, and 1, and that we've done here. So we then move ahead to compute the determinant of AZ. So, and that we've done here, working on the minors, the determinant of the minors, and playing around matrix AZ to compute the determinant of AZ shows that the determinant of AZ gives 46. So what we then do using Cramer's rule is to divide the determinant of AX by the determinant of A to get variable X, and that gives us 8 all over 11. And we also use the Cramer's rule to divide to say determinant of AY all over determinant of A, and to get Z, the determinant of AZ minus the determinant of A. So doing that shows that variable X becomes 8 all over 11, variable Y becomes Y all over 11, 9 all over 11, and variable Z gives us 49 all over 11. So you can compare this answer to using other methods of solving systems of linear equation and see that the answers are all the same. Alright, so far in this lecture, we have considered analytical methods for solving systems of linear equation, and the methods considered are substitution method, elimination method, Gaussian elimination method, matrix inversion method, and Cramer's rule. And I believe the explanations are very, very clear, and you should be able to solve systems of linear equations using any or all of these methods.